going to speak about axiomatizing complete positivity.
Thanks very much. Good morning. Does this go to work? Yeah, okay. So, in quantum mechanics, the systems we deal with, we think of them as being Hilbert spaces. In this talk, I'm going to talk about finite dimensional Hilbert spaces, because, well, just for simplicity. And the morphisms between them, the processes of the unitary maps, that we're just going to think about the non-normalized versions, so just linear maps. And so this gives you a dagger compact symmetric modal category. And I'll explain what that means later, but I think it's already been covered in several previous talks. So yeah, that's the category of quantum systems and the pure maps between them. And in this talk, I'm going to talk about introducing mixed states, ones which have some kind of probabilistic nature to them. So there's some uncertainty about what they do to each state. And there's two different ways that people have come up with for modelling this. One of them is CPM, and you just have the same objects, the finite dimensional Hilbert spaces, and you take the morphisms to be the complete positive maps. So that means that your states are the density matrices, and the morphisms are the maps which preserve density matrices. And then another way of doing it is with CP star, which is the category of the C star algebras. And you can have the C star algebras include all the quantum things and also classical systems as well. And again, you can define what it means to have a completely positive map between two C star algebras. And so we have these inclusions. So C lives inside its CPM, which lives inside its CP star. And that's because any pure map is also a mixed map. And all of the quantum systems, which are these ones, give you C star algebras. And then the C star algebras also have classical ones. So this is a strict inclusion. So yeah, C star algebras can be classical or quantum and various things in between. And so that's what happens if we apply CPM or CP star to the category of finite dimensional Hilbert spaces. And in fact, this generalizes to functors CPM or CP star, which you can apply to any dagger compact symmetric monoidal category. And so there's a question you can ask, which is, given a category, when is it equal to CPM or CP star applied to some other category? And it would be good to answer this question, because then if we wanted to talk about a category which had morphisms and mixing, we wouldn't have to say take a category of pure morphisms and then apply CPM or CP star. We could just say take a category which obeys these axioms, and that would be a sort of nicer way to do it. So yeah, I've got some slides which say what it means to be symmetrically monoidal and compact and dagger. I think we've seen most of this already. I'll just go with the example of finite dimensional Hilbert spaces. So the objects are Hilbert spaces, the morphisms are linear maps, and you can compose them. And then the tensor product is the monoidal product. And you can extend this to morphisms, and that's just doing two processes in parallel. And there's a canonical map which swaps two processes, which swaps two systems over. And then a compact category, each object has to have a dual, which is the dual vector space in this example. And there's a canonical map from the scalars to something tensor difference dual, which is, well, it's the map which picks out the identity. So something tensor difference dual is isomorphic to the endomorphisms, and there's a canonical endomorphism which is the identity, and that just picks it out. And we also have the cap, which is the trace, takes an endomorphism, just gives you its trace. And these two things, let's just define the transpose of the map, which is this thing and we denote it by rotating the morphism around, as though we'd taken this diagram and pulled these two lines straight. And FD Hill is also a dagger category, which means it has a functor which we think of as turning a thing upside down, and in this case it's just the Hermitian adjoint. That gives you a contravariant functor. And so for any morphism we have 4 different versions of it, depending on its given by all its possible orientations. Okay, so now we can talk about some mixing. So in quantum mechanics, the mixed states are given by the positive matrices, which is precisely the ones of that form. And like I said earlier, I'm not going to worry about normalization, and so we don't have to say trace 1 or anything. We just can take any positive matrix. And we want to think about, I'm thinking of morphisms going up the board. And so when we have a positive matrix like this, we bend one of the wires around to give you something like this. And so a mixed state is precisely the same as a state of rule of A, tensor of A, one of that form. And then you can talk about completely positive morphisms, and the tri-down isomorphism says that they're precisely the ones of this form. Alternatively, you can think of this as being spline spring dilation or the Krauss maps. Those 3 things are already the same. So what this says is you can think of a general mixed thing as being starting with the system, applying some function, and then tracing out part of the answer and just looking at the remainder. And there's a shorthand for this where those are board lines.
Does anyone know?
Yeah. So the general map is one of this form. Instead of drawing this, we can draw this. And so, because basically this way of writing things is redundant because the left-hand side is always the same as the right-hand side. And so we just imagine folding everything in half. And so we can write things as this, and then this is a discarding map, which represents tracing out. And so, so this is the CPM construction. And so you can apply it to an arbitrary diagonal at symmetric reliable category. It doesn't have to be symmetric, but it makes them simpler. It doesn't have to be compact, but that also makes them simpler. So the objects are the same as the ones you already had, and the morphisms from A to B are perhaps this form. And your original category of pure maps embeds by just the, this is just F and you don't discard anything. Or in this shorthand, you just be taking F to itself. Okay, so now we can look at our question. Given a category C, when is it the CPM or something? And this is already answered by Bob. And the answer is that if you have a C and you can find some subcategory, which is a subcategory you want to be the pure maps, and each object has one of these discarding maps, and they satisfy these axioms, then in fact your category is isomorphic to the CPM of the pure subcategory that you identified. And this axiom just says that the discarding map respects the monoidal product and the dagger in the sort of way you'd expect. And this one says that the discarding map does what we want it to do, i.e. if we've got 2 representations of the same morphism as applying something and then discarding it, that's because they're the same in this sense. And then our final axiom is what's called the purification axiom, and it says that any morphism in your big category can be represented as a pure morphism with something discarded. Okay, and how would we prove this? well, because of, I've written these the wrong way around, but because of the purification, every morphism in C is something of this form, and the morphisms in CPM and CPure are something of this form, and the bijection between them is precisely this shorthand which I wrote up here. And the axioms that we had before are just precisely what you need to show that this is a functor, is a well-defined functors between axiometric and module categories. Yeah. So now we're going to talk about C-star algebras, and they correspond to special Dagger Frobenius structures, which we've already seen a lot about. Things which specify these axioms. And so in finite dimensional Hilbert spaces, these correspond precisely to the finite dimensional C-star algebras. And so a C-star algebra is a vector space with a multiplication defined on it, an identity, and this is precisely this. And then there's also a star, which takes an element of your vector space and it's an involution of your vector space. And that's given by I goes to its conjugate with that map writer. And so that gives you the correspondence between Frobenius structures and C-star algebras. Although it's finite dimensional, so we could have said star algebras, and we could have said the Neumann algebras, and it made any difference. So a state is positive when it's of this form, something multiplied by its conjugate. And because we've got the arrows on the lines, we don't need to keep track of inputs and outputs. So when we've got something of this, we'll happily draw it like this. We'll bend one of the wires around to make it easier to draw. So the positive state's the ones of that form. And you can prove in a similar way to Trojan-Pawlowski that the complete positive morphisms are things of this form. And so compose any diagonal symmetric model category. The objects will be these special Dagger Frobenius algebras, and the morphisms will be these completely positive maps. And then there are these important Frobenius algebras called pair of Hans algebras, where for any object A, we get a algebra on A dual times A, where the multiplication is this, and the unit is this, where I should get the arrows right. Like that. And okay, I'm lying to you slightly because this isn't special. If I was to draw another one here, it would nearly be this if we have this loop in the middle. But provided our category is sufficiently nice, we can find some normalizing thing which gets rid of this. We call that a completely positive, positive dimensional category, which means we can normalize it. Okay, so we looked for a completely positive map between two of these things. It would be something of something of this form. Because of course, all of these wires between it can be combined into one big wire. So we see that the complete positive maps between these algebras are precisely the ones we already had in CPM. So this gives our inclusion CPM to CP star. Of course, our original category is in CPM. So in the case of Hilbert spaces, these are the C star algebras corresponding to the quantum systems, and the rest of them correspond to classical systems and things which are mixed between quantum and classical. So I want to axiomatize it, and at first I couldn't quite see how the axiomatization was going to work, because I wanted to talk about these multiplication maps inside CP star, but I couldn't because they're not themselves completely positive. But eventually I saw that this map is completely positive when you consider it as a map from the quantum system on both the objects to the C star algebra that you care about. And so you can sort of think of this as, so here's the main theorem of the paper. It's tells you when a category is C star of something, and of course because CPM lives in it, we still have these discarding maps, and now we also have some extra maps which go from a pure thing, which is one of the complete quantum C star algebras, to an arbitrary one. And the way to think of these is like decoherence. So you have a quantum system and it maps into a classical system by forgetting the things which aren't on the diagonal of the density matrix. Or going the other way, you have a classical system and and you think of it as a quantum system just by forgetting whatever classical structure you had on it. Just thinking of it in the quantum way. And so we still have the same axioms for the discarding map. Now we have these new maps, the decoherent structure, and again they have to respect the monoidal product. And we have these two equations here, which this one says if you have a classical thing, you go to the quantum thing, but then you go to the classical thing again, it's the same as not doing anything. And this one says if you have a quantum thing and you decohere it onto a classical structure and then take it back to the quantum thing again, that's the same as this thing, where this is your original multiplication map. The way to think of that is like if you make a clone of something in the basis corresponding to that classical structure, and then you observe it, that's precisely the map which decoheres your classical structure down, your quantum structure down onto that classical basis. And then again we have a purification axiom which says any mixed map can be thought of starting in C star algebra, going to a quantum system, applying some pure map, and then discarding part of it, and then going back to the C star algebra you want to end up in.
Sorry, in the case of the C star algebras, what would F sub A typically be? So A is a
So
F of A is a, yeah, what's the, run through that example?
So for each, so we've identified a subcategory C pure in our category, which is the one we want it to be CP star. And then for each Frobenius algebra in C pure, we have to identify an object in our big category, which we think is the one corresponding to that C star algebra.
I just want to know what's the right way to do it in the standard example, in the most familiar example, which I would imagine would be when.
Sure, so we have so if C was the category of C star algebras, in since we usually think of them, and then C pure would be Hill. And so if you have a special dagger for Frobenius algebra right here, that gives you a C star algebra. So this map takes something to the algebra here, the pair of pants algebra, and then this F then takes the special Frobenius things in here to F, to their corresponding C star algebra. And so yeah, again, everything has a purification. You can write those just in terms of a pure map between two quantum systems. And again, the isomorphism is this sort of folding in half thing. So you can imagine this, when you fold in half, this dot becomes this arrow, and this dot becomes this one. And tracing out here is still with this dot map here. And the axioms are precisely the facts that you need to show that this is a isomorphism of Cash-based. That's it.
Okay. Are there any other questions? Yes?
Am I right in assuming that that triangle map over there is the abstract equivalent of the embedding of a sister algebra into an algebra of operators? Is that the intuition behind this?
So that's certainly true when your C-star algebra is a classical algebra.
It's still, why wouldn't it? Because that algebra that you described with the pair of pants is basically an algebra of matrices over some semi-range, I guess.
If what you said was true, we hope that for this thing, that arrow would be the identity. It's just
Yeah.
betting onto us.
Yeah, because
But it's not. In fact, it ends up in here.
no. I mean, it's an embedding. I'm not saying it's necessarily the traditional embedding. It need not be the identity.
Okay, yeah, sure.
Yeah,
It is.
it's
Yeah.
some embedding
Yeah.
that has nice properties. And okay.
Jamie?
So to show that a category is with the form CP star, you need to put a lot of structure on that.
Yeah.
Find lots of structure on that category.
Yeah. In particular, you have to do all the work of finding the pure subcategory
Right.
yourself.
So if I just give you some category,
No, I'm stumped. Yeah.
I mean, you could in general find it very hard to either find this structure or prove that structure could not be
Yeah.
found, right? So I'm asking, when you go beyond the traditional examples, how useful this approach actually is.
So I think it's useful because you at least know what you're looking for.
Sure, well,
Yeah.
that helps.
Yeah.
But it may be,
You have to for each object, we have to find one of these triangular maps.
right, but I'm asking if in practice it's possible to actually find this with or not. We looked at some exotic examples. I think it'd be nice to know that hills wasn't which forms C star or something like that. For example, that seems plausible.
So I've proved that hill isn't the CP star of some other category.
You
But
actually proved that.
I have managed to prove that, but I don't think I've yet managed to prove that rail isn't the CP star. So that's what I'm working out at the moment is trying to find an actual inverse for CP star, something which is like an inverse. Given the C, we would actually identify the CPF for you. That would be ideal. Yeah.
More explicit.
Any more questions? Yeah.
Just one of John's question for an example of M2. Could you say what would that be F? So 2 by 2 matrices is a C-star algebra which just comes from the number space. So what is F?
So what? So I can quite hear.
I'm just asking for a concrete example of an A or an A.
Okay, so
Just doesn't make sense algebra.
I'm not sure we have time for a whole example.
okay, well, I can show you later on.